Have you ever wondered what the sky looks like on other planets and moons? Today we're taking a journey through our solar system to explore the skies of different celestial bodies. Imagine standing on a world light years away, or even just a few planetary neighbors over and looking up. Would you see a familiar blue, or something entirely different, something that challenges your very definition of sky? The universe, my friends, is not monolithic in its presentation. Each planet, each moon, tells a unique story through the canvas above it, painted by the laws of physics and the specific ingredients of its atmosphere, or lack thereof. This isn't just a sightseeing tour, it's an exploration into the very nature of light, atmosphere, and perception. The color of a sky, the visibility of stars, the appearance of the sun, these are all clues, cosmic breadcrumbs leading us to understand the environment of these distant worlds. From the crushing pressures of Venus to the tenuous haze of Pluto, the view from the ground looking up is a profound indicator of the conditions that prevail. So buckle up, cosmic travelers. We're about to embark on an extraordinary voyage, peeling back the layers of alien atmospheres to witness vistas that have, until now, largely existed only in the realm of scientific calculation and artistic imagination. Our journey will take us from the sun-scorched inner planets to the icy realms of the outer solar system, and even to some fascinating moons that boast skies as intriguing as any planet. We'll delve into the science behind why these skies appear as they do, the scattering of light, the chemical compositions, the density of gases. It's a reminder that the Earth's blue sky, so familiar and comforting, is just one of countless possibilities in the grand cosmic tapestry. Prepare to have your perspective shifted, your curiosity ignited, and your appreciation for the diversity of our solar system deepened. Let's begin. Our first stop is Mercury, the innermost planet, a world of extreme temperatures and a sky that offers a stark, unfiltered view of the cosmos. But on Mercury, the concept of sky as we know it barely exists. The planet is so close to the sun and has such a weak gravitational pull that it can only hold onto a vanishingly thin layer of gas called an exosphere. This exosphere is composed of atoms blasted off the surface by solar wind and micrometeoroid impacts. What does this mean for an observer on Mercury's surface? It means the sky is predominantly black, an inky void stretching endlessly above. Even during the Mercurian day, with the sun blazing fiercely, the heavens would not illuminate with color. The sun itself would appear about 2.5 times larger, and significantly brighter than it does from Earth. Without a substantial atmosphere to scatter sunlight, there's no diffusion of light, no blue hue, no gentle transition from day to night. It's a realm of sharp contrasts, blindingly bright sunlit surfaces and pitch-black shadows. Imagine standing on that sun-baked, cratered terrain. Above you, the stars would be visible even with the sun in the sky. This lack of atmospheric scattering also means that there are no traditional sunrises or sunsets with changing colors. Next, we venture to Venus, Earth's so-called twin in size, but a world with a sky that could not be more different or more hostile. If Mercury's sky is defined by its absence, Venus's sky is defined by its oppressive presence. This planet is shrouded in an incredibly thick atmosphere, about 90 times more massive than Earth's, composed primarily of carbon dioxide with clouds of sulfuric acid. This dense blanket creates a runaway greenhouse effect, making Venus the hottest planet in our solar system, with surface temperatures that can melt lead. From the surface of Venus, assuming you could survive the crushing pressure and searing heat, the sky would appear a murky, sulfurous yellow or yellowish orange. This color is due to the way sulfur particles in the thick clouds absorb blue light and scatter yellow and orange wavelengths. The sunlight that filters through this dense, acidic cloud deck is diffuse and dim. You wouldn't see the sun as a distinct disk, but rather as a brighter patch in the hazy, overcast sky, a perpetual gloom that offers little variation. The clouds are so thick and permanent that you would never see stars, other planets, or even the sun clearly. Let's step away from planetary atmospheres for a moment and visit our closest celestial companion, Earth's moon. The sky from the moon is, in many ways, similar to what you'd experience on Mercury, but with one rather spectacular addition. Like Mercury, the moon has no significant atmosphere to speak of. Its exosphere is even more tenuous. This means that once again the sky is a deep, velvety black, regardless of whether the sun is shining or not. Imagine standing on the dusty gray plains of the moon. During the lunar day, which lasts for about 2 Earth weeks, the sun blazes in that black sky, casting incredibly sharp, dark shadows. There's no atmospheric scattering to diffuse the light, so the contrast between sunlit areas and shadowed areas is extreme. The lunar surface itself would be brilliantly illuminated, but look up, and it's the void of space, punctuated by the fierce light of the sun. And just as on Mercury, the stars would be visible even in broad daylight, unwavering points of light against the black backdrop. But the truly breathtaking feature in the moon's sky is, of course, the Earth. Our next destination is Mars, the red planet, a world that has captivated human imagination for centuries. Unlike Mercury and the Moon, Mars does possess an atmosphere, albeit a thin one, about 1% the density of Earth's. This tenuous atmosphere, composed mainly of carbon dioxide with traces of nitrogen and argon, is just substantial enough to create a visible sky, but it's a sky quite different from our own. The Martian sky is typically a butterscotch or pinkish-red color during the day. This distinctive hue isn't primarily due to the composition of the gases themselves, but rather to the presence of fine particles of iron oxide dust, essentially rust, suspended in the atmosphere. These dust particles are kicked up from the Martian surface by winds and can remain aloft for extended periods. They preferentially scatter red light forward, giving the sky its characteristic reddish tint when you look away from the sun, and a yellowish or butterscotch color closer to the sun. While the daytime sky is reddish, Martian sunrises and sunsets offer a surprising twist. They are blue. We now venture into the realm of the gas giants, starting with the colossal Jupiter. Jupiter's surface is the tops of its vibrant and turbulent cloud layers. The visible clouds are organized into distinct bands, dark belts and lighter zones. These are formed by powerful jet streams and convective currents. The clouds are composed of different chemicals at different altitudes. Continuing our journey through the outer solar system, we arrive at Saturn, the jewel of our solar system, famous for its spectacular system of rings. Like Jupiter, Saturn is a gas giant, predominantly composed of hydrogen and helium, with a similarly layered atmosphere. However, Saturn's overall appearance, and thus its sky, tends to be more subdued in color compared to Jupiter's vibrant display. The upper atmosphere of Saturn is characterized by a thick haze layer, and its clouds are formed deeper down and are less distinct than Jupiter's, giving the planet a more uniform pale yellowish or golden-brown hue. This coloration is primarily due to ammonia ice crystals in the upper cloud deck, similar to Jupiter, but perhaps with different trace chemicals or a different temperature profile affecting their appearance. The overlying haze scatters sunlight, contributing to a softer, more muted look. If you were an observer floating within Saturn's upper atmosphere, the sky above would likely appear as a bright, hazy expanse, perhaps a pale yellow or butterscotch color. The sunlight would be significantly dimmer here than at Earth or even Jupiter, given Saturn's greater distance from the sun. This dimmer illumination, combined with the scattering effect of the haze, would create a sky that feels vast and somewhat diffuse. Our next port of call is not a planet, but Saturn's largest moon, Titan, a truly extraordinary world with a thick nitrogen-rich atmosphere denser than Earth's. This makes Titan unique among moons in our solar system, and its sky is unlike any other we've encountered. It's a world shrouded in a thick orange haze, a consequence of complex atmospheric chemistry. The atmosphere of Titan is about 95% nitrogen, with the remainder being primarily methane and other hydrocarbons. Sunlight and high-energy particles from Saturn's magnetosphere interact with methane and nitrogen in the upper atmosphere, breaking them down and reforming them into a complex soup of organic molecules. These molecules, collectively known as tholins, form a thick, planet-circling smog or haze that gives Titan's sky its characteristic deep orange or brownish-orange color. From the surface of Titan, the sun would be a very dim object, perhaps only appearing as a slightly brighter area in the thick, hazy orange sky, if visible at all as a distinct disk. The amount of sunlight reaching the surface is only about 1/1000th of what Earth receives, making daytime on Titan perpetually twilight-like. We now journey further into the cold, dim outer reaches of our solar system to Uranus, one of the ice giants. Uranus, along with its sibling Neptune, has a sky that presents a distinct and beautiful color, quite different from the gas giants Jupiter and Saturn, and certainly different from the terrestrial worlds. The sky of Uranus is a lovely shade of cyan, or blue-green. This distinctive coloration is primarily due to the presence of methane in its atmosphere. Uranus's atmosphere is composed mainly of hydrogen and helium like Jupiter and Saturn, but it contains a higher proportion of ices like water, ammonia, and methane. Methane gas is particularly good at absorbing red and orange wavelengths of sunlight, while reflecting blue and green light back into space, and thus to our eyes, or to an observer within its upper atmosphere. If you could float in the upper cloud layers of Uranus, the sky above would appear as a serene, almost featureless expanse of pale blue-green. Unlike Jupiter with its dramatic belts and zones, Uranus's atmosphere appears remarkably bland in visible light from a distance, though closer inspection and observations in other wavelengths reveal subtle cloud bands, storms, and convective features. Our penultimate planetary stop is Neptune, the most distant true planet from our Sun, and the other ice giant in our solar system. Like Uranus, Neptune's atmosphere is primarily hydrogen and helium, with a significant amount of methane. And like Uranus, methane is the key ingredient that gives Neptune's sky its striking color. However, Neptune's blue is a much deeper, more vibrant azure compared to Uranus's paler cyan. The reason for Neptune's richer blue color is still a subject of scientific investigation. While methane is certainly responsible for absorbing red light, the intensity of the blue suggests that other factors might be at play. Perhaps the methane is concentrated at different altitudes, or there's another, as yet unidentified atmospheric component that contributes to the scattering or absorption of light. It's also possible that Neptune's atmosphere is clearer of haze at the altitudes where the blue color originates, allowing for a more profound scattering effect. Our final destination takes us to the Kuiper Belt, to the dwarf planet Pluto. Pluto, once the 9th planet, has a complex atmosphere of nitrogen, methane, and carbon monoxide. It freezes and sublimates as Pluto orbits the Sun. New Horizons revealed Pluto's sky is blue, due to sunlight scattering off tholins. Standing on Pluto, you'd see a pale, hazy blue sky. Our grand tour of alien skies comes to a close. From Mercury and our moon, to the yellow veil of Venus, and the rusty blush of Mars, to the majestic gas giants, we've seen diverse celestial canvases. Each sky tells a unique story. The universe is rich with variety. Thanks for joining us on this journey. Like, subscribe, and hit the bell icon for more space content. Keep exploring with us. See you next time.